Hey guys, I'm going to wait a few more minutes to let everybody else trickle in, and then we'll get started. All right, we've got a few people probably still going to trickle in, and we'll let them in as we're going, but in an effort to, um, not take advantage of everybody's time, we'll go ahead and get started. I did want to introduce myself. I'm Kimberly Lupo, founder of Portrait Pharmaceuticals. We're an analytical testing laboratory located in Wilmington, North Carolina. Um, and so I'm going to take my camera off for the duration of the presentation. But I just wanted to say hello. But thank you so much for joining me today as we discuss method lifecycle management. Uh, we're going to be going through the 5 phases of method lifecycle. First, the method development, then validation, next method transfer, followed by routine use and continuous verification. And then finally, after FDA approval, product approval, with method updates and lifecycle management. We should have some time after the presentation for Q&A. So if you have any questions throughout the talk, please add to the chat and we will address them at the end. So before we dive into the technical details, let's just address why method lifecycle management matters to your organization and why it should matter to your leadership. First is cost. The financial impact is significant. A single failed transfer can cost $200,000 to $500,000 when you factor in investigation, repeat work, manufacturing delays, and lost revenue. Post-approval changes cost 10 to 50 times more than getting it right during development. Lifecycle thinking is about being proactive rather than reactive. The next thing is compliance. This isn't optional anymore. ICH Q2 and Q14 explicitly emphasizes lifecycle approaches. Regulatory agencies now expect to see an ATP, an MODR, and continuous verification documentation. Companies with strong lifecycle management see significantly fewer 483 observations. And then lastly, continuity, perhaps the most important for day-to-day operations. Lifecycle management ensures your methods perform consistently over time. Knowledge isn't lost when people leave. Method transfers smoothly between sites, and troubleshooting is faster because you have documented method knowledge. So we're going to start at the analytical target profile, or ATP. And this is really the foundation that everything else in method lifecycle management is built on. And a lot of companies don't integrate it into their process. So what is an ATP? It's a simple prospective statement of what your method needs to do, not how it does it, but what performance it needs to deliver to support the decisions you're making. Think of it as the method equivalent of a product's target product profile. Before you design a drug, you define what it needs to achieve clinically. The ATP does the exact same thing for your analytical method. So why do we start here? The most common mistake I see in method development is jumping straight to the instrument. Someone walks up to the HPLC, starts running samples, and figures out the method as they go. The ATP forces you to stop and ask, what problem am I actually solving? What range do I need to measure? How precise do I really need to be? And what's in the sample that can interfere? When you define those expectations up front, every subsequent decision in development has a clear target to aim for. And when you get to validation, you're not guessing at acceptance criteria. They flow directly from the ATP you've already wrote. The first is its intended purpose. It's not enough to say this method measures the purity of the API. You need to capture the full context. Is this for release testing or stability? Is this drug product or drug substance? Is it supporting a regulatory submission? Is it just for process control, or both? The intended purpose defines the stakes, and the stakes defined how tight your performance requirements need to be. The second element is reportable range. This is the range of concentrations, or in the case of an assay, percentages of label claim over which your method must perform reliably. For a typical small molecule assay, you're usually looking at something 80 to 120% to cover both your release specifications and your stability samples. But getting this right matters because your linearity studies, your accuracy experiments, and your entire validation scope is anchored to this range. And the third element is the sample matrix. And this is where I think a lot of people get into trouble. The matrix isn't just the tablet or the API powder. It's a detailed description of everything in that sample that could affect your measurement, like excipients, solvents, process residuals, degradation products, packaging, extractables, if that's relevant. And so why does this matter? Because a method that works beautifully on pure reference standard can completely fall apart when you inject a real tablet or extract full, or a real tablet that is full of binders, fillers, and lubricants. Defining the matrix up front means you're designing and testing specifically against the actual analytical challenge, not just an idealized version of it. So when you bring these three elements together, you have a document that genuinely guides your development work rather than just sitting in a filing system. So here's some snips from an example ATP for a generic acetaminophen tablets, 500 milligram assay method. And as you can see, it's fairly simple, but it contains all of the relevant information needed to proceed to development. If you put your email address in the chat, I can send out a blank template to everyone after the presentation so that you can use and potentially integrate into your processes. So now you have your ATP is defined, you have a clear picture of where you're trying to land. So how do you build a method that reliably gets you there? And how will it hold up to real world conditions? That's the essence of a knowledge-driven development. Rather than running experiments until something works and calling it done, you're systematically building an understanding of why it works. That understanding is what protects you during transfer, during routine use, and when a regulatory asks you to justify your method parameters. So let's start how we identify risk before we even run our first experiment. Two tools come up repeatedly and in an analytical risk assessment, and that I'm sure we've all done them, and they complement each other very well. The first is the fishbone diagram. And the idea is very straightforward. You start with your outcome on the right and you work backwards, brainstorming every category of input that could cause that outcome. So like for an OOS instance, it could be sample preparation, mobile phase, column temp, instrument calibration, analyst technique, diluent stability. And so the fishbone is great for generating a comprehensive list of potential failure modes. What it doesn't do well is tell you which of these risks actually matter. That's where the failure mode and effects analysis comes in, the FMEA. You take the risk you identified in the fishbone and score it, each one across 3 dimensions. How likely is this failure to occur? How severe would the impact be if it did? And how detectable is it? Would you even know if it happened? So multiply those scores together and you get a risk priority number and for each failure mode. And then the items with the highest number becomes your focus. This matters because it keeps your development work focused. You're prioritizing the variables that could actually compromise the analytical results for your ATP demands. So how do we actually investigate those high-risk parameters? And this is where I want to challenge the habit, and I'm bad about this myself. The traditional approach is OVAT, or one variable at a time. You hold everything constant, change one parameter, observe the effect, reset, change the next one, and so on. It's intuitive, it's easy to explain, but it's rigorous. The problem is that it's not. OVAT misses something fundamental: interactions between parameters. For example, the effect of change in your mobile phase pH often depends on your column temperature. If you only ever change one thing at a time, you'll never see those interactions. And you can build a method that looks perfectly robust in development, but falls apart the moment the 2 parameters drift simultaneously in a real lab. So that's why you have design of experiments. Instead of changing one variable at a time, you systematically vary multiple parameters together in a structured way. A well-designed experiment would say 5 or 6 factors that can be completed in a fraction of the runs that OVAT would require, and it gives you something OVAT never can: a mathematical model of how your method responds across a multi-dimensional parameter space. That model is your method operable design region, which we'll go over in detail shortly. But the important point here is that the DOE isn't just more efficient, it produces better knowledge. You understand not just what each parameter does individually, but how they behave together. And that understanding is exactly what ICH Q14 is asking you to demonstrate. The outcome of your risk assessments and your DOE experiments is a classification of your method parameters. And getting this classification right is important because it shapes everything that follows: your MODR boundaries, your system suit criteria, your transfer protocol, and your routine monitoring plan. A critical method parameter is one where variation within a practically feasible range has a meaningful impact on method performance relative to your ATP criteria. Think of something like mobile phase pH in a separation that depends on ionization state. A shift of even 0.2 pH units could move your resolution below your ATP threshold. So that's a critical parameter. It needs tight control. It needs to be included in your system suit approach, and it needs to be clearly specified in your method. A non-critical parameter is one where you've demonstrated through your DOE that variation across a realistic range doesn't meaningfully compromise performance. You still specify in your method, but you don't need to control it with the same rigor, and you're not tying up your system suitability requirements around it. So getting the classification documented clearly with the experimental evidence behind it is what gives you a defensible, science-based foundation for your MODR. So now we have a rich data set describing how your method responds across a range of parameter combinations. The MODR is how we translate that data set into something operationally useful. MODR is one of those terms that gets used loosely, but the multidimensional space of method parameter values within which the method consistently meets the performance criteria that you defined in the ATP. Every combination of parameters inside that space delivers a result that satisfies your accuracy, precision, specificity, and range requirements. Step outside of that space and you can no longer guarantee that performance. That definition is important because it frames the MODR not as a regulatory deliverable, but as a genuine operational tool. It tells you exactly how much flexibility you have and exactly where your boundaries are. So both traditional robustness and MODR involve deliberately varying method parameters and observing the effect, but the underlying philosophy is fundamentally different. Traditional robustness testing is essentially a pass-fail exercise. You make a small defined change to your parameters one at a time, check your method still passes your system suit criteria, and document that it's robust. MODR thinking is a little different because it's continuous rather than binary, and it's multivariate. You're not asking, does the method survive a plus or minus 0.1 change in pH? You're building a model that tells you the full response surface, the shape of the method, performance across the entire parameter space. You know not just whether the method is robust, but how robust, where it starts to degrade, and which combinations of parameters approach the edge of the acceptable performance. With MODR data, your working ranges are scientifically justified. You can demonstrate to a regulator exactly why your pH is controlled to plus or minus 0.05 units rather than plus or minus 0.1 units, because you have the data showing what happens at plus or minus 0.1, and it approaches your ATP boundary. So that brings me to system suitability. And this is an area where I think we all could do a lot better. The traditional approach to system suitability criteria is somewhat circular and often arbitrary. You run your validation, you observe the performance you get under optimized conditions, and then you set your system suit limits based on what you observed, typically adding a small margin. The result is system suitability criteria that tell you your method is performing the way it performed during validation under controlled conditions. What they don't necessarily tell you is whether your method is performing well enough to deliver reliable results for its intended purpose. When your system suit criteria are derived from your MODR boundaries rather than from observed validation performance, they become more meaningful. Your resolution criteria isn't greater than 2.0 because that's what we saw during validation. It's greater than 2.0 because your DOE demonstrated that below 2.0, the method begins to fail the specificity criteria in your ATP, particularly under the sample matrix conditions that we defined. That's a completely different level of scientific justification, and I think that's what ICH Q14 is pushing the industry toward. It also makes your system suit criteria more defensible in 3 situations that every analytical lab faces: method transfer, troubleshooting, continuous verification. With your ATP defined, our method parameters characterized, and our MODR established, we now have everything we need to design a validation strategy that's genuinely fit for purpose. The term validation often conjures up this image of a massive, rigid, checklist-driven exercise. ICH Q2 is pushing us towards something a little bit smarter, fit-for-purpose validation. The rigor of your validation should match the risk and the decision-making weight of the method. Not every method needs the full battery of tests. Not every parameter needs the same level of scrutiny. What matters is that your validation demonstrates fitness for the specific intended purpose you defined in your ATP. There are the classic validation parameters: specificity, linearity, accuracy, precision, etc. These are still foundational, but what has changed is how we think about applying them. The revision 2 of ICH Q2 introduced a helpful framework that defines the method categories. So category 1 methods are quantitative assays for major components. Think API content in drug product or purity determination in drug substance. These are high stakes measurements that directly determine whether a batch passes or fails. release. You need tight precision, tight accuracy, demonstrated specificity, and robust performance across the full reportable range. Category 2 methods are for impurities. These methods typically operate at a much lower concentration in the analytical range. The challenge is different. Your precision targets are relaxed compared to category 1, but your LOQ and specificity requirements are more stringent because you're trying to detect and quantify trace level components in a complex matrix. Category 3 covers performance tests like dissolution and content uniformity. The validation requirements here depend heavily on whether the tests are quantitative or qualitative and what the specification limits look like. Category 4 are identification tests. These are typically limit tests or yes/no determinations, and the validation is way more simpler. The key insight is that validation isn't one size fits all. A category 2 impurities method doesn't need the same precision performance as a category 1 assay. And attempting to force it into that mold wastes resources and often results in unrealistic acceptance criteria that cause problems downstream. The second dimension of right sizing is the development phase. The validation you do for phase 1 clinical method is not and should not be the same as what you would do for a commercial NDA method. In early development, you're often doing what's called method qualification rather than full validation. You demonstrate the method is suitable for its intended use at that stage, but you accept that things may change. Your reportable range might be wider, your precision might be adequate rather than tight, and you're not necessarily stress testing every conceivable failure because the method itself might evolve as your formulation or process changes. But late phase 2 and certainly phase 3, you're moving towards full validation because regulatory submission is on the horizon. And at this point, stability indicating capability is critical. Your MODR is well defined and your validation report is being written with an eye toward what will go into your module 3 of your submission. The bottom line is this: right sizing your validation saves time, saves money, and paradoxically often results in better quality methods because you're focusing validation resources where they actually matter rather than generating data just for its own sake. So when do you need to do full validation, and when can you get away with just verification? Full validation covers all applicable parameters comprehensively. Verification focuses on the parameters most likely to be affected by whatever changed. The decision tree should be, has the fundamental method performance changed? Has your ATP changed? Has your sample matrix meaningfully changed? If yes to any of those, you need to do full validation. If you're essentially confirming that an established method behaves as expected under slightly different conditions, verification is probably appropriate. And here's where your MODR knowledge becomes very valuable. If the change you're making, say switching to a slightly different HPLC column from your same manufacturer, is within your validated MODR space, verification is clearly justified. You already have demonstrated acceptable performance across that parameter range. And if the change takes you outside of your MODR, then you're into revalidation territory. So let's talk about a couple of places where validation goes wrong. I'm going to focus on 3 big ones that cause the most pain downstream: unrealistic acceptance criteria, insufficient specificity evaluation, and misapplication of statistics for precision and accuracy. The first pitfall is setting acceptance criteria that are tighter than what they need to be. So here's what happens. You run your validation under carefully controlled conditions. Everything is fresh reagents, freshly calibrated instrument, experienced analyst who knows the methods inside and out, ideal laboratory environment. You get beautiful data. Precision comes in at 0.5% RSD. Recovery is 99.5 to 100.5. Resolution is 3.5 when your ATP only requires 2.0. And then someone says, great, let's get our acceptance criteria based on what we achieve. So you write in your method, precision must be less than 0.7% RSD, accuracy has to be between 99 and 101, and your resolution has to be greater than 3.0. Well, then you just kind of set yourself up for failure because then the method gets run in a different building, in a different instrument, with a different water source, a different analyst, reagents that are not new, and everything. So everything is still within its validated parameter space, and nothing has really gone wrong, but now the precision is running at 1.2% RSD, and recovery is 98.5 to 101.5. The root cause is that you set your system criteria on what you observed under ideal conditions rather than what you need for the method to be fit for purpose. Your acceptance criteria should be based on your ATP requirements, not your validation performance. The second major pitfall is insufficient specificity in evaluation. Specificity is your method's ability to measure the analyte unequivocally in the presence of everything else that could be there. Not just what's there at time zero, but what develops over time as your product degrades, as your formulation ages, and as stress conditions create new impurities that weren't present during development. So here's what the inadequate approach is. Specificity is demonstrated by injecting the API, injecting each known impurity individually, and showing that they're all separated. The problem is if you only demonstrated specificity against things you expect to see, you haven't demonstrated specificity against what you didn't expect. And stability studies are where the unexpected happens. So an ICH Q1A R2 is very clear that for stability indicating methods, you need forced degradation studies. You need to stress your product under acid-base, oxidation, thermal, and photolytic conditions and demonstrate that your method can separate and quantify the API in the presence of all the degradation products that form under those conditions, not just the ones that you anticipated. So comprehensive forced degradation on a representative formulation samples evaluated not just for separation, but for peak purity using DAD or mass spec. The final pitfall is misapplication of statistics for precision and accuracy. And this one's a little bit more technical. So for precision, the typical approach is to prepare 6 replicates, measure them, calculate the percent RSD, and compare it to your acceptance criteria. The source of those replicants matters enormously. If you evaluate repeatability, same analyst, same day, same instrument, your 6 replicants need to truly be independent measurements. That means 6 separate sample preparations, not one prep injected 6 times. And for intermediate precision, you need to incorporate the sources of variability that will be present in routine use. So different analysts, different days, different instruments, or lots of columns and reagents. A common design is 2 analysts, 2 days, 2 preparations per analyst per day. That gives you 8 measurements that capture realistic variability. Then you use analysis of variance to partition the variance and understand how much is coming from each source. So now we'll move on to accuracy. The standard approach is to spike known amounts of analyte into your sample matrix at 3 concentration levels and calculate percent recovery. Spiking pure API into a placebo matrix tells whether your method can quantitatively recover the API when there's no API present to begin with. That's useful, but it's not the same as demonstrating accuracy when you're quantifying API in a real sample with the full complement of excipients and background matrix at realistic levels. Additionally, when you're evaluating accuracy, you don't calculate the mean recovery and check it within its range. If it's within your range, you need to look at your confidence interval. If your mean recovery is 99.5, but your 95% confidence level is 97 to 102, then you have individual measurements falling outside of your acceptance range, even though your mean is fine. So you've got your method validated. You may need to transfer your method to another lab. And the foundation of a successful method transfer is a well-designed protocol. And the first decision you need to make is what type of transfer are you doing? There's 2 approaches, and the most common is the comparative transfer, is where where the sending lab and the receiving lab both test the same samples using the validated method, and then you compare the results statistically. If the results are equivalent, then within the predefined acceptance criteria, the transfer passes. So this is just a straightforward approach, and it directly answers the question labs often care about. Can the receiving lab site, the receiving lab reproduce our results. The disadvantage is that it requires coordination between site, and it only tells you the method works on those specific samples. So co-validation is an alternative. The receiving lab performs an abbreviated validation using their own equipment and their own analyst and their own samples. They're independently demonstrating that the method performs according to the ATP requirements in their hands. Co-validation takes more resources, but is often a smarter choice when you're transferring to a lab with significantly different instrumentation or infrastructure, when the method is highly complex or technically challenging, and when the regulatory sensitivity around the transfer is there. Or even when you're transferring early in development and you expect the method might still evolve. Having the receiving lab demonstrate full capability gives you more confidence than a simple comparison study. The design details can make or break transfers, regardless of which way you go with the design. The number of analysts, you need at least 2 qualified analysts at the receiving site. If one analyst gets acceptable results and the other doesn't, you've learned something important about whether the method is truly transferable or whether it's just transferable to one specific person. And that's the kind of risk you want to uncover during transfer, not 6 months later during routine testing and you have OSs or out of trends. The number of replicants are also important. For comparative transfer, the typical design is 3 to 6 replicates per analyst. That gives you enough data to assess precision at the receiving site and to make a statistical comparison between sites. The number of lots is something that I don't think we as labs and sponsors consider. We need at least 3 different sample lots in your transfer study. Why 3? Because if you only test one, and the results agree, you've demonstrated that the labs can get the same answer on that specific lot. You haven't demonstrated that they'll get the same answer on a different lot with a slightly different matrix characteristics or impurity profiles. You want at least 1 lot at the low end of your specification range, 1 at the high, and 1 in the middle. And if you're transferring an impurities method, include at least 1 lot with elevated impurities. Don't just transfer pristine batches where there's nothing to detect. Statistical acceptance criteria, this is where your MODR knowledge pays off. Your transfer acceptance criteria should be based on your validated method performance, not on some arbitrary standard. Your acceptance criteria needs to account for the expected variability of the method, plus the additional variability introduced by site-to-site differences. The typical approach for comparative transfer is to use equivalence testing. You define an equivalence margin, often based on your intermediate precision, and you demonstrate statistically that the difference between sites falls within that margin. For most assay methods, an equivalence margin of plus or minus 3 to 5% is reasonable if your method precision supports it. So before you even start the formal transfer, there's some pre-transfer activities that dramatically improve your success rate. Equipment qualification. Confirm that the receiving site equipment is appropriately qualified for the method. Second is analyst training. The receiving lab's analysts need to be trained on the method by someone from the sending lab who's actually run it successfully. Of course, reagent and reference standard qualification. Confirm that the receiving lab has the same reagents, or if not, that their reagents are equivalent. And pay particular attention to critical reagents. And then you have trial runs. Before a formal transfer, have the receiving lab do informal trial runs to work out any kinks. Even with perfect planning, method transfers run into challenges. A common one is equipment differences between sites, so adjuvant versus waters, HPLC, water quality, solvent purity, buffer pH. Those all can vary site to site. Back in my metrics days, we had a method we were transferring to California, and the pH of the water in California was 2 pH units lower than ours, and we were failing the transfer. So all those things you kind of have to consider up front. So when a transfer fails, the investigation definitely needs to be methodical and not random. So start with your MODR knowledge, what parameters are critical, what performance changed, um, was it resolution, retention time, peak shape, match the symptom to the likely cause, and of course, document everything. So the method is transferred, it's up and running at a new site, and now we move into the longest phase of the life cycle, which is just routine use. A method that performs beautifully during validation doesn't automatically keep performing beautifully for the next 10 years. Equipment drift, columns change, reagent lots change, analyst turnover, environmental conditions vary. And all of these factors, individually small, can accumulate over time and push your method towards the edge of the acceptable performance or even past it. So we'll start with system suitability testing. As we've said before, your system suit criteria should be derived from your ATP requirements and your MODR boundaries, not from your validation performance. So what do you need to prove to confirm your method is performing correctly? Reference standard and reagent control. Reference standards need to be qualified, stored appropriately, tracked for expiry, and verified for suitability before use. Reagents need to be fresh and prepared according to the specification. Any buffer pH needs, they need to be verified when prepared, not just assumed. The mobile phase need to be filtered and degassed if your method requires it. And diluents need to be checked for compatibility and stability. These are common GMP, but they can also be root causes when the method starts to drift. So we'll talk about deviations, or sometimes we would consider some of these OOSs or out of trends. No method runs perfectly 100% of the time. Equipment fails, people make mistakes, reagents degrade. A minor deviation is one that's unlikely to impact the quality of the result and don't compromise the analytical result's validity. A major deviation is one that could reasonably impact the result's validity or patient safety. These, of course, require rigorous investigation and potentially impact assessments before you can use the results. The key is having clear criteria in your quality system for what constitutes major versus minor. Every deviation, even minor ones, needs to be documented. For major deviations or recurring patterns of minor deviations, your CAPA should include a root cause analysis. Pay attention to patterns. One deviation is an incident, 3 similar deviations in 3 months is a trend, 5 deviations across multiple methods involving the same equipment is a systemic issue. Sometimes a pattern of deviations is telling you that the method itself is a problem. It's too complex, too sensitive to small variations, not robust enough for routine use. That brings us to routine use and continuous verification. Because system suit tells you about today's performance, but trending tells you about the trajectory of your method over time. And I think this is where a lot of labs don't they kind of fail the verification piece of this. So any trajectory helps you intervene before you hit a real problem. So trending precision and accuracy over time. Your method's precision and accuracy aren't static. They vary from batch to batch, analyst to analyst, day to day. What you want to know is that variation random noise, or is there a systematic trend? For precision, you should be tracking the variability of your control samples, or like your standard check standards over time. Plot the RSD week by week or month by month. If your method validated at 1.5% RSD and you're consistently running 1.2 to 1.8, you're fine. That's within normal variability. The method is performing as expected. But if you see a trend where the RSD is creeping up 1.5, then 1.7, all the way to 2.2, that's a signal something is drifting and you need to investigate before it hits your alert limit. The same logic applies to accuracy. Track the recovery over time. If you validated at 99 to 101 and you're consistently getting within that range, that's great. But if you're seeing a trend toward 98.5, then 98.0, and then even lower, you're drifting towards a potential OOS threshold. So it's time to investigate. Control charts and statistical process control. So this is where formal statistical process control techniques come in. And I think they're underutilized in analytical labs. So a simple Levy-Jennings chart or a Shewhart chart, control chart, can give you powerful insight into whether your method is in control or drifting out of control. Essentially, you establish your center line, the mean performance of your method based off of your historical data. You establish your control limits, typically plus or minus 2 standard deviations and plus or minus 3 standard deviations from the mean. Then you plot every new result as it comes in. If your results are bouncing around within the plus or minus 2 standard deviation limits, your method is in control. And that's normal random variation. But if you see patterns, 8 consecutive points on one side of the center line, 2 points outside of the plus or minus 2 standard deviations, is a clear upward or downward trend. And those signals, and that signals that something's changed. The method isn't behaving the way it used to, and you need to find out why. And the beauty of control charts is they catch drift early. You don't wait until you get an OOS result to realize something is wrong. And also, if you trend it as it goes, when you do get an OOS, you don't have to spend a lot of time going back and tabulating all of that data, investigating it. You already have it available to you. So you see the trend developing and you intervene while results are still within spec. And that's, like I said, proactive quality control. So when does a drift in signal a need for method improvement? So if the drift is caused by something transient, a bad reagent, a temporary equipment issue, an analyst who needs retraining, then you just fix it and the method returns to its previous performance. That's handled as a OS or an investigation, and you have corrective action. You document it and you move on. But if the drift is systematic and persistent, maybe the column performance is degrading faster than expected, maybe your reference standard stability is worse than you thought, or your instrument technology has changed and your method is on the edge of what older equipment can reliably deliver. That's a signal that you need method improvement or a method change. So you don't want to keep band-aiding a method that's clearly struggling. So that's when you think about modernization or replacement. Eventually, you will need to make changes, or because there's an opportunity to improve it, or because regulatory or business requirements have shifted. So this is the final phase of the method life cycle, and with a commercial product, it can even last decades. And it's where life cycle thinking really separates mature organizations from reactive ones. So science advances, technology improves, regulatory expectations evolve, business needs change. So we'll break down 3 major topics: post-approval changes, method improvement opportunities, and eventually method retirement. Once your method is in an approved filing, any change to that method has regulatory implications. You can't just decide to switch from HPLC to UPLC because it's faster, or change your column because the old one is discontinued without thinking through the regulatory pathway. Prior approval changes are the most significant and typically take 4 to 6 months, sometimes longer, to implement or to get approval for. Examples would be switching from HPLC to a completely different technique like capillary electrophoresis or mass spec, or adding it or removing an impurity specification, significantly widening your acceptance criteria in a way that could potentially allow lower quality products to pass. Then you have CBE 30, which means you submit the supplement, wait 30 days, and if the agency doesn't object, you can implement the change. These are moderate changes and don't require full prior review. Some examples might include changing to a different column with the equivalent performance, modifying sample preparation slightly while maintaining the same analytical principle, or updating your method to a newer version of the same technique, like moving from HPLC to UPLC with demonstrated equivalency. And then you have CVE 0, which means you can implement the change immediately and report it in your next annual report. These are very minor changes with minimal quality impact. Comparability protocols are your tool here. You take representative samples, ideally samples that span your specification range, and include some with elevated impurities or degradation, and you test them with both the old method and the new method. Then you perform a statistical comparison to show equivalence. While post-approval, pre-approval changes can feel like a burden, strategic method improvements can deliver real business value. Implementing enhanced methods like UPLC, modern core shell columns, improved detectors like a CAD or high-resolution mass spec can offer significant advantages like faster runtimes, better resolution, lower solvent consumption, reduced environmental impacts. So implementing enhanced methods post-approval requires regulatory justification. You just need to make the business case internally, and you need to make the scientific case to the agency. The business case could include throughput gains, cost savings, compliance and risk reduction, or just strategic alignment. From a regulatory perspective, the hurdle for method improvement is demonstrating that the enhanced method maintains the same level of control or better than the legacy method. The typical approach is a side-by-side bridging study to demonstrate one of two things. First, equivalence. The method must give the same answer within your predefined comparability margin. It tells the agency, we're not changing what we know about the product, we're just measuring it a little bit more efficiently. And then secondly, it's non-inferior. The new method performs as well or better than the old method. Maybe resolution improves from 2.2 to 3.5, or maybe the precision improves from 8% RSD to 4%. So you're demonstrating enhanced control, not just equivalent control. But don't try to bridge methods that are too different. If you're going from just a regular HPLC UV finish to LC mass spec with a completely different separation chemistry, that's not a bridge. That's a new method and needs full validation and will likely need prior approval. Bridging works when the analytical principle is fundamentally the same and you're making technological improvements within that principle. So when do you retire an old method? You should consider retiring a method when the product it supports has been discontinued and you're past your final stability time points. The method has been replaced by a superior method. The bridging is complete and all historical data has been generated with the old method. And there's no regulatory or business reason to maintain both. The method is so outdated. Maybe its uses hazardous reagents that are being phased out, or depends on equipment that is no longer supported by the manufacturer. Or the frequency of deviations and failures is so high that the method is consuming a disproportionate resources relative to its value. You can't just delete a method and walk away. You must have documentation of the method, archive all of its raw data and results, and document and communicate the archival to the relevant people. So we walked through the 5 phases of development with ATP and MODR, fit for purpose validation, and transfers, continuous verification during routine use, and thoughtful management of changes and retirement. So when you think in terms of life cycle rather than isolated events, everything connects. Your ATP drives your development decisions, your MODR informs your validation acceptance criteria and your system suit limits. Your validation data supports your transfer protocol, and your routine trending identifies improvement opportunities. Your improvement projects are executed with regulatory strategy in mind, and the benefits are real. Reduced costs from fewer failures and faster cycle times, better compliance from science-based documentation and proactive control, and true continuity from knowledge that's captured and accessible through methods lifecycle. So just remember ICH Q2 and Q4 aren't just regulatory requirements. They're a roadmap that's building and maintaining analytical methods that actually work in development and manufacturing across sites. And that's the goal. So that's why Lifecycle matters. We do have just a few minutes before Q&A, so if anything that we've discussed today resonates with challenges you're facing in your own labs, that's exactly what we do at Portrait Pharmaceuticals. We're a contract analytical lab that focuses on small molecule testing, and we built our entire model around life cycle thinking. What sets us apart is speed without shortcuts. We guarantee 3-week turnaround times while maintaining CGMP compliance and regulatory readiness. So if your program needs analytical support that keeps pace with your timelines, I would love to have a conversation, but we'll stop the little sales pitch, and if you have any questions. Let's see. Does anybody have any questions? All right. Well, I wanted to thank you guys again for attending this webinar. I hope it was helpful and that you were able to get something out of it. And please connect with me if you have any further questions or want to take anything offline. And so I just want to say thank you again, and I hope you have a great week.
Thank you.